I'm so glad you could make it tonight. You found Science Blanket, your quiet space for wonder. Have you ever looked at a cloud and felt like you were looking at a slow-motion dream? Tonight, we're wrapping ourselves in the science of the sky, specifically the gentle, drifting life of clouds. We often think of them as solid objects, but they are actually ghosts of the atmosphere. Trillions of tiny water droplets or ice crystals suspended in a delicate balance between the earth and the void. From the high, wispy cirrus clouds that look like pulled silk to the heavy, grey blankets that bring the rain, clouds are the visible signature of the air's invisible movement. As we begin, imagine yourself floating on a high, white peak of a cumulus cloud, feeling as weightless as the mist itself. You don't need to understand the physics of evaporation or the names of the altitudes tonight. Just let the slow drift of the sky tuck you in. If this blanket of atmosphere helps you find rest, I'd love for you to subscribe and join our community of sleepy explorers. Now, take a slow, deep breath. Feel your lungs expand and then empty, as steady as a breeze. Let the weight of your day evaporate into the night air. Relax your jaw, let your shoulders drop, and sink into the softness of your bed. Let's explore the quiet wonders of the clouds together. Imagine standing in the middle of an endless ocean at night, holding a lantern that illuminates the water around you in a perfect circle. Everything within that circle of light is visible to you, but beyond it, the ocean continues into darkness. This is remarkably similar to our situation in the cosmos. The observable universe forms a sphere around Earth, extending roughly 46.5 billion light-years in every direction. That means if you could measure from one edge of what we can see, through Earth, and out to the opposite edge, you'd find yourself looking at a distance of about 93 billion light-years. It's a number so large that it defies easy comprehension, a span so vast that if you started counting seconds and each second represented a light year, you'd be counting for nearly 3,000 human lifetimes just to reach the halfway point. But here's where things start to feel a bit strange, a bit like a cosmic puzzle that doesn't quite fit together at first glance. Our universe is only about 13.8 billion years old. We know this from multiple lines of evidence, from the cosmic microwave background radiation that fills space to the ages of the oldest stars we can find. So if the universe has only existed for 13.8 billion years, how can we possibly see things that are 46.5 billion light-years away? Light, after all, travels at a fixed speed, the fastest speed possible in our universe. Nothing can outpace it. So shouldn't the farthest thing we could possibly see be only 13.8 billion light-years distant? It seems like the math doesn't work, like the universe is somehow cheating at its own rules. The answer lies in something both elegant and mind-bending. Space itself has been expanding while light was traveling toward us. Picture an ant walking across the surface of a balloon while someone slowly inflates it. The ant is moving at a steady pace, but the surface beneath its feet is stretching. By the time the ant reaches its destination, the balloon has grown larger, and the distance it has actually covered is greater than you'd expect from simply multiplying its walking speed by the time elapsed. Light traveling through the universe faces the same situation. A galaxy emitted light toward us billions of years ago, and that light began its journey across space. But during those billions of years, space itself expanded, stretching the fabric of the cosmos and carrying that galaxy farther and farther away from us even as its ancient light continued moving in our direction. This means something remarkable and slightly unsettling. The objects we see near the edge of the observable universe, the most distant galaxies our telescopes can detect, are not where they appear to be. When we look at a galaxy whose light has traveled for 13 billion years to reach us, we're seeing where that galaxy was 13 billion years ago. But during those 13 billion years, the expansion of space has carried that galaxy much farther away. Today, right now, that same galaxy might be more than 40 billion light-years distant, far beyond the reach of its ancient light that we're only now receiving. It's like watching a ship sail away on the ocean while looking through a telescope that somehow shows you where the ship was hours ago. The image you're seeing is real, but it's also a ghost, a memory of a place that no longer exists in that location. This creates an important distinction that astronomers are careful to make. There's the observable universe, which is everything we can see, everything whose light has had time to reach us since the beginning. And then there's the entire universe, the totality of everything that exists, which could be something else entirely. The observable universe is like that circle of lantern light on the dark ocean. It's real, it's measurable, and we can study it in incredible detail. But the entire universe, the full extent of reality beyond what we can observe, remains mysterious. We don't know how big it is. We don't know if it has an edge or if it goes on forever. We're confined to our sphere of visibility, looking outward and wondering what lies in the darkness beyond. The entire universe could be vastly larger than what we can see. In fact, based on our understanding of cosmic inflation, the brief period of exponential expansion that occurred in the first fraction of a second after the Big Bang, the full universe might be unimaginably larger than our observable bubble. Some calculations suggest it could be orders of magnitude bigger, perhaps thousands or millions or even infinite times the size of the observable portion. Imagine you're sitting in a small room with a single window, and through that window you can see a garden. You might naturally wonder, does the garden end just beyond what I can see, or does it continue for miles? Does the property extend to the horizon, or am I looking at a tiny fraction of a vast estate? We face the same question with the universe, except the window is our observable sphere and the garden is all of reality. Space may extend far beyond the observable universe, continuing in all directions with more galaxies, more stars, more planets, more of everything we see around us, or perhaps containing structures and features we haven't even imagined. There's no reason to think that space suddenly stops at the edge of what we can observe. That would be like assuming the ocean ends at the horizon simply because you can't see beyond it. The light from those distant regions simply hasn't had time to reach us yet. Remember, the universe is only 13.8 billion years old, and even though space has been expanding all that time, there are still places so far away that their light hasn't completed the journey to Earth. Every moment, new light is arriving from slightly more distant sources, expanding our view by tiny increments, but there will always be places beyond our reach, regions of space whose light won't arrive for billions more years, if ever. When people talk about the edge of the universe, when they ask whether space ends somewhere out there in the cosmic void, they're usually referring to the observable boundary without realizing it. It's an understandable confusion. We use phrases like the edge of the universe in everyday conversation, in documentaries and articles, and it's easy to imagine this as a physical place, perhaps a wall or a barrier where space simply stops. But that observable boundary isn't an edge in any physical sense. It's simply the limit of how far we can see, determined by the age of the universe and the speed of light. It's a horizon, not a border. Stand at the edge of a flat plain and you'll see the horizon perhaps 3 or 4 miles away, where the curvature of the Earth cuts off your view. But that horizon isn't a wall. Walk toward it and it moves with you, always maintaining the same distance. The edge of the observable universe works similarly, except the curvature is created by the combination of light speed and cosmic time rather than Earth's geometry. And here's perhaps the most important thing: there is no evidence of a physical wall where space stops. No observation suggests that if you could somehow travel to the edge of the observable universe and then keep going, you'd eventually hit a barrier or find yourself at the end of everything. Every indication we have from physics suggests that space either continues indefinitely or curves back on itself in ways that make the question of an edge meaningless, like asking what's north of the North Pole. The universe doesn't appear to have a center or an edge in the traditional sense. Every point in space looks roughly the same, with galaxies stretching away in all directions, growing more distant and more redshifted the farther out you look. If there were a true edge to space, we'd expect to see some asymmetry, some direction in which things looked fundamentally different. But we don't see that. The cosmos appears roughly uniform in all directions, suggesting that if you could view the universe from any other galaxy billions of light years away, you'd see something remarkably similar to what we see from Earth: a sphere of observable space surrounded by darkness, with no indication of where the center might be or whether an edge exists at all. The universe creates its own boundaries, not through walls or barriers, but through the fundamental limitations of information itself. Because of cosmic expansion and the finite speed at which light travels, horizons exist in the universe much like they exist on Earth's surface, except these cosmic horizons are far more profound in their implications. When you stand on a beach and look toward the ocean, the horizon marks the farthest point you can see before the curve of the planet blocks your view. Something similar happens in the cosmos, but instead of planetary curvature creating the limit, it's the interplay between time, distance, and the relentless stretching of space itself that draws these invisible boundaries around us. The particle horizon defines the current boundary of the observable universe, that sphere extending roughly 46.5 billion light-years in all directions from Earth. It represents the farthest distance from which light has had time to reach us since the beginning of everything. Think of it as a growing bubble of visibility. When the universe was very young, this bubble was small because light hadn't had much time to travel. As time passes and the universe ages, more light from more distant sources completes its long journey to our telescopes and our eyes. The particle horizon grows over time as more light reaches observers, expanding our view incrementally with each passing moment. Right now, as you listen to these words, light that has been traveling for billions of years is arriving at Earth for the first time. Light from galaxies that were previously beyond our particle horizon, now finally visible after their photons completed a journey of unimaginable duration. But there's another horizon, one that's more troubling and more permanent. A cosmic event horizon marks regions that can never affect us, places in the universe that are receding so quickly due to cosmic expansion that even if they sent a signal toward us today, that signal would never arrive. This isn't because space is particularly far away in the traditional sense, but because the expansion of the universe itself is carrying those regions away from us faster than light can close the gap. It's like trying to swim upstream in a river that flows faster than you can swim. No matter how hard you try, how fast you move, you'll never make progress toward your destination. You'll only be swept farther and farther backward. This cosmic event horizon lies about 16 billion light-years away, a distance that sounds smaller than the observable universe but represents something far more absolute. Everything beyond this boundary is fundamentally disconnected from us. We might see some of these regions because we're looking at ancient light they emitted long ago when they were closer, when the expansion rate hadn't yet carried them beyond this critical distance. But anything happening in those places now, any events occurring beyond the event horizon at this very moment, will never be visible to us. Their light will never reach us. Their influence will never touch our corner of space. They exist in a separate realm of reality, observable perhaps in the past tense through ancient light, but completely isolated from our future. What makes this horizon so significant, what transformed it from a temporary boundary into a permanent barrier, is dark energy. This mysterious component causes the universe's expansion to accelerate, and it appears to make up roughly 70% of everything that exists. Dark energy acts like an anti-gravity force, pushing space apart with ever-increasing vigor. For most of the universe's history, expansion was slowing down. The mutual gravitational attraction of all matter was acting as a brake, decelerating the expansion even though it couldn't stop it entirely. But about 5 or 6 billion years ago, something changed. The universe had expanded enough that matter became sufficiently diluted, and dark energy, which doesn't thin out as space expands, began to dominate. From that point forward, expansion started accelerating instead of decelerating, and it's been speeding up ever since. This acceleration further limits what can ever be observed because it ensures that the cosmic event horizon remains fixed at a finite distance. In a universe without dark energy, where expansion was slowing down, the event horizon might not exist at all. Eventually, given enough time, light from any galaxy, no matter how distant, could theoretically reach us. But in an accelerating universe, there are places whose light will simply never arrive. The expansion is too fast, the acceleration too relentless. These distant regions slip away from us at ever-increasing speeds, receding into an isolation that will never be broken. And the effects of this acceleration will become more pronounced as time goes on. Future galaxies will redshift beyond visibility, their light stretched to such extreme wavelengths by the expansion of space that even our most sensitive instruments won't be able to detect them. Redshift occurs when light travels through expanding space. As space stretches, the wavelengths of light stretch with it, shifting visible light toward the red end of the spectrum and beyond, into infrared, microwave, and eventually radio wavelengths so long that the light effectively disappears into the cosmic background. Galaxies that we can see today will fade from view over billions of years, not because anything happens to them, but because the space between us and them expands so much that their light becomes undetectable. They'll still be there, still shining, still filled with stars and planets and perhaps life, but they'll be invisible to any observer in our galaxy, lost beyond a horizon of expansion. Eventually, only the local group will remain visible. The local group is our cosmic neighborhood, a collection of galaxies including the Milky Way, Andromeda, and several dozen smaller galaxies, all bound together by mutual gravity. These galaxies are close enough that their gravitational attraction to each other overcomes the expansion of space. They're not receding from us. In fact, Andromeda is actually moving toward us and will eventually collide and merge with the Milky Way in about 4 billion years. The local group represents a gravitationally bound island in the expanding cosmos, and as the universe continues to age and accelerate its expansion, everything outside this island will eventually redshift beyond detectability. Future astronomers, living trillions of years from now in the merged galaxy that was once the Milky Way and Andromeda, will look up at a sky containing only the stars of their own local group. All other galaxies will have vanished from view, receded so far that their light can no longer reach these distant observers. Those future astronomers, unless they have access to our historical records, might conclude that their galaxy is the entire universe, surrounded by empty space extending infinitely in all directions. It's a sobering thought, this idea that the universe is gradually isolating us, drawing curtains of distance and acceleration that will eventually hide most of reality from view. We live in a special time, cosmologically speaking, a moment when the universe is old enough that we can see the cosmic microwave background radiation, the afterglow of the Big Bang, but young enough that we can still observe distant galaxies and study the large-scale structure of the cosmos. This window of visibility won't remain open forever. But perhaps the most counterintuitive aspect of cosmic expansion is what it doesn't mean. Cosmic expansion does not mean space expands into an external void. This is one of the most common misconceptions about the universe, the idea that space is like a balloon inflating into a room, pushing outward into some pre-existing emptiness. But there is no room. There is no external void. Space itself is all there is. When we say the universe is expanding, we mean that the distances between galaxies are increasing, that the fabric of space itself is stretching, adding more space between objects without those objects necessarily moving through space in the traditional sense. It's not that galaxies are flying apart through a static void. It's that new space is constantly being created between them, and this creation of space is what we call expansion. There's nothing outside the universe for it to expand into, because outside is a concept that only makes sense within space, and space is the universe. The universe isn't expanding into anything. It's simply becoming larger, creating more of itself, more space, more distance, more room for matter and energy to occupy. The universe follows rules, patterns that emerge when you step back far enough to see the grand design. The expansion rate of the universe follows Hubble's law, a relationship discovered in the late 1920s by astronomer Edwin Hubble when he noticed something peculiar about distant galaxies. They were all moving away from us, and not just moving away randomly, but following a specific pattern. The farther away a galaxy was, the faster it appeared to be receding. This wasn't a coincidence or a quirk of our local neighborhood. It was a fundamental property of the cosmos itself, a mathematical relationship that connected distance and velocity in a surprisingly simple way. For every additional million parsecs of distance, roughly 3.25 million light-years, a galaxy's recession velocity increased by a predictable amount. More distant galaxies recede faster than closer ones, and this relationship holds true across the entire observable universe. A galaxy a billion light-years away recedes at a certain speed. A galaxy 2 billion light-years away recedes twice as fast. A galaxy 10 billion light-years away recedes 10 times as fast. It's a linear relationship, at least at distances where we can measure it accurately, and it tells us something profound about the nature of cosmic expansion. If galaxies were simply flying apart through static space, launched by some primordial explosion, we wouldn't see this pattern. Objects launched from an explosion move at different speeds depending on the force that propelled them, not on how far they've traveled. Some would be fast, some slow, scattered randomly across space with no particular correlation between their distance and velocity. But this recession is due to expanding space, not motion through space, and that makes all the difference. Galaxies aren't racing through the universe like cars on a highway. They're more like raisins in rising bread dough. As the dough expands, the raisins move apart from each other, not because they're moving through the dough, but because the dough itself is growing, creating more space between them. The farther apart two raisins are, the more dough exists between them, and therefore the more new dough is created as the bread rises, pushing them apart faster. Replace dough with space and raisins with galaxies, and you have cosmic expansion. Each galaxy remains relatively stationary within its local patch of space, but the space itself stretches, carrying galaxies away from each other at rates proportional to their separation. This understanding leads to an important philosophical and observational principle about the universe. The cosmological principle states the universe is homogeneous on large scales, meaning that if you look at sufficiently large volumes of space, they all contain roughly the same amount of stuff arranged in roughly the same way. This doesn't mean every cubic light-year is identical. Obviously, some places have stars, some have planets, some are empty space. Even on larger scales, matter clumps into galaxies, and galaxies gather into clusters and superclusters. But zoom out far enough, look at regions hundreds of millions of light-years across, and a pattern of uniformity emerges. The average density of matter, the distribution of galaxies, the overall structure, all become statistically similar no matter where you look. The universe is also isotropic, looking the same in every direction. Turn your telescope north, south, east, west, up, down, and you'll see the same general picture. Galaxies scattered through space, some close, some distant, arranged in clusters and filaments and voids, but with no preferred direction, no axis along which things look fundamentally different. This isotropy is closely related to homogeneity. If the universe is the same everywhere, it should naturally look the same in all directions from any vantage point. These properties, homogeneity and isotropy, are pillars of modern cosmology, assumptions that allow us to apply the same physical laws throughout the universe and trust that our observations from Earth represent universal truths rather than local quirks. One of the most important consequences of these principles is that no location is a special center of the universe. This idea can be difficult to grasp because our everyday experience is filled with centers. Cities have downtowns, countries have capitals, solar systems have suns at their center. When we observe that all galaxies are receding from us, that the universe appears to expand outward in all directions with Earth at the apparent center of the motion, it's tempting to conclude that we occupy a privileged position, that we're somehow at the middle of everything. But this is an illusion created by the nature of expansion itself. Remember the raisin bread analogy. If you were a conscious being living on one of those raisins as the dough expands, you would observe all other raisins moving away from you. The ones twice as far would recede twice as fast. You would appear to be at the center of the expansion. But a being on any other raisin would observe exactly the same thing from their perspective. Each raisin, each galaxy, sees itself as the apparent center, not because any of them truly are central, but because expansion happens uniformly everywhere. Earth is not at the center of cosmic expansion, and neither is the Milky Way, or the local group, or any other structure in the universe. The concept of a center only makes sense for objects expanding into something else, like a balloon inflating in a room where you could point to the balloon center in relation to the walls. But the universe isn't expanding into anything external. There's no cosmic room with walls. There's only space itself, stretching uniformly, and from any point within that space, the expansion appears centered on you. It's a perspective effect, a consequence of living inside the thing that's expanding rather than observing it from outside. When we examine the universe on those truly large scales where homogeneity becomes apparent, we find that large regions statistically contain similar galaxy structures. A volume of space a billion light-years across in one part of the universe contains roughly the same number of galaxies as an equivalent volume elsewhere. The galaxies themselves might be different, their individual stars and planets unique, but the overall count, the total mass, the general arrangement, these properties remain remarkably consistent. It's like comparing different cubic meters of ocean water. The specific water molecules are different, the particular dissolved salts might vary slightly, but the average density, salinity, and composition stay within a narrow range no matter where you sample. This uniformity extends to the largest structures we can observe. Cosmic voids and filaments repeat on immense scales throughout the universe. Voids are vast regions, sometimes hundreds of millions of light-years across, containing very few galaxies. They're not completely empty, but they're remarkably underdense compared to the cosmic average. Filaments are the opposite, elongated structures where galaxies congregate, stretched across the universe like strands in a cosmic web. These filaments connect galaxy clusters, creating a network of matter that defines the large-scale structure of the universe. And what's remarkable is that this web-like pattern, this distribution of voids and filaments, repeats everywhere. Look at one section of the universe and you'll see this structure. Look at another section billions of light-years away and you'll see essentially the same thing, a different arrangement of the same basic pattern, like different sections of an infinite fractal displaying similar features at every scale. This supports a uniform large-scale structure and reinforces our confidence in the cosmological principle. If the universe were chaotic or random, if different regions had fundamentally different properties or arrangements, we wouldn't see this repetition. The fact that the cosmic web looks essentially the same everywhere we observe it, that voids and filaments and galaxy clusters appear in similar proportions and configurations no matter where we point our telescopes, tells us something profound. It tells us that the same physical processes shape the entire universe, that the same initial conditions existed everywhere, and that no region is special or fundamentally different from any other. We live in a cosmos that is, on the largest scales, remarkably democratic and uniform, a universe without borders or centers or edges in any meaningful sense, where every place is effectively equivalent to every other place when viewed from sufficient distance. It's both humbling and strangely comforting, this realization that we occupy no special position, that the universe extends in all directions following the same rules, governed by the same forces, displaying the same grand architecture wherever conscious beings might arise to observe it. When we try to understand the shape of the universe itself, we enter territory that challenges our intuition in fundamental ways. Measurements show the universe is very close to geometrically flat, a discovery that has emerged from decades of increasingly precise observations of the cosmic microwave background radiation and the distribution of galaxies across space. Flatness, in this context, doesn't mean the universe is a pancake or a sheet. It means that the geometry of space follows the rules we learned in high school, the Euclidean geometry where parallel lines never meet, where the angles of a triangle always sum to exactly 180 degrees, where the circumference of a circle is always pi times its diameter. These relationships seem obvious because they describe the space we experience in our everyday lives, but there's no fundamental requirement that the universe follow these rules on cosmic scales. Space could curve in ways that alter these basic geometric relationships, and for a long time, we didn't know which type of geometry described our universe. Flatness is consistent with an infinite universe, though it doesn't prove infinity conclusively. If you have a flat geometry, a space where Euclidean rules apply everywhere, that space can extend forever in all directions without encountering any contradictions or boundaries. Think of an infinite flat plane stretching endlessly. There's no point where it has to stop or fold back on itself. You could travel in any direction forever and never reach an edge. The same principle applies to three-dimensional flat space. If the universe is truly flat in its geometry, it could be infinite in extent, containing an infinite number of galaxies, an infinite amount of matter and energy, structures, and worlds without end. The mathematical relationship is actually quite specific. If space has zero or negative curvature, it can extend without end. Zero curvature is the flat geometry we just described. Negative curvature is something different, stranger, a geometry where space bends away from itself in a particular way. Negative curvature resembles a saddle-shaped geometry, like the curved surface you'd find on a horse's saddle or a Pringle chip, where the surface curves upward in one direction and downward in another. In such a universe, parallel lines would eventually diverge, moving farther apart as they extend into the distance. The angles of a triangle would sum to less than 180 degrees. A circle circumference would be greater than pi times its diameter. These might sound like mathematical abstractions, but they represent genuinely different possible shapes for the fabric of reality itself. Both flat and negatively curved universes share an important property: they can be infinite. There's no geometric requirement for them to close back on themselves or to have boundaries. They can simply continue forever, an endless expanse of space governed by consistent geometric rules but never repeating, never looping back, just extending outward without limit in all directions. Our measurements suggest we live in a universe very close to flat, possibly exactly flat within the limits of our ability to measure, which means infinity remains a real possibility. But there's another option, a different type of curvature that leads to profoundly different conclusions. Positive curvature would resemble a higher dimensional sphere, similar to how the surface of Earth is a two-dimensional sphere embedded in three-dimensional space. On a positively curved surface, parallel lines eventually converge and meet. The angles of a triangle sum to more than 180 degrees. A circle circumference is less than pi times its diameter. If our three-dimensional universe has positive curvature, it would curve back on itself in a fourth spatial dimension we can't directly perceive, forming a closed shape, a three-dimensional analog of a sphere's surface. This leads to a remarkable possibility. A finite universe does not require an edge. This statement seems contradictory at first. How can something be finite, limited in extent, without having a boundary where it ends? The answer lies in topology, the mathematical study of shapes and spaces. Consider the surface of a sphere, like Earth. It has a finite area. You could measure it, calculate it, and arrive at a specific number of square miles or square kilometers. Yet it has no edge, no boundary, no point where the surface suddenly stops. Space could wrap around on itself like a sphere's surface, curving through dimensions we can't visualize to connect back to itself seamlessly. If the universe has this topology, traveling far enough might return you to your starting point, assuming you could somehow travel faster than the universe expands and live long enough to complete the journey. You'd head off in one direction through space, moving in what appears to be a straight line, never turning, never changing course, and after traversing an unimaginable distance, you'd arrive back where you started from the opposite direction. It would be like ancient sailors circumnavigating Earth, proving that the world was round not by finding an edge, but by returning home from an unexpected direction. Such a universe would still lack boundaries. There would be no wall to hit, no sign saying end of universe, no point where space simply stops existing. Every location would be surrounded by more space in all directions, yet the total volume would be finite, a closed three-dimensional surface wrapping around through higher dimensions. Interestingly, there are multiple possible topologies for a finite universe beyond just the simple spherical one. Space could connect to itself in more complex ways, creating structures with names like 3 torus or Poincare dodecahedral space, shapes where traveling in certain directions brings you back to familiar territory but perhaps reflected or rotated in ways that would create patterns in the distribution of galaxies or the cosmic microwave background. Astronomers have searched for evidence of these topologies, looking for repeated patterns that might indicate we're seeing the same structures from multiple angles, light that has wrapped around the universe to reach us from different directions. So far, these searches have found nothing conclusive. This brings us to perhaps the most honest statement we can make about the universe's extent. Present data cannot distinguish infinite from extremely large finite space. Our observations show the universe is very flat, so close to zero curvature that any deviation is smaller than our instruments can detect. If there is curvature, if the universe does curve back on itself, that curvature is so slight that the universe must be vastly larger than the observable portion. Imagine trying to determine whether you're standing on a flat plane or an enormous sphere. If the sphere is large enough, millions of times larger than your horizon, the curvature within your visible area would be too subtle to measure. You'd see what appears to be flat ground in every direction, unable to determine whether it continues flat forever or eventually curves back after distances far beyond your view. We face the same limitation with the universe. The observable universe spans 93 billion light-years, an almost incomprehensible distance. Yet if the total universe is thousands or millions of times larger, if it curves back on itself only at scales we cannot observe, we'd see exactly what we do see: apparent flatness, no detectable curvature, no evidence of topology, just space extending uniformly in all directions following Euclidean geometry as far as our instruments can measure. The universe could be infinite, extending forever with no repetition and no boundary. Or it could be finite but so immense that we occupy a tiny fraction of it, too small a sample to detect the overall shape. Both possibilities remain consistent with everything we've observed, and we may never be able to determine which is correct, living as we do with a fundamentally limited view of a cosmos that extends far beyond the reach of our most powerful telescopes. The quest to determine the shape of the universe has become increasingly precise over the past few decades, thanks largely to our ability to study the oldest light in existence. Cosmic microwave background measurements constrain spatial curvature tightly, providing us with the most accurate data we have about the overall geometry of space. This radiation, the afterglow of the Big Bang itself, fills the entire universe with microwaves that have been traveling through space for over 13 billion years. When we map the tiny temperature variations in this radiation, variations that amount to only millionths of a degree, we're seeing imprints of conditions in the early universe, patterns that reveal fundamental properties about the nature of space itself. These patterns are sensitive to curvature. If space were significantly curved, either positively like a sphere or negatively like a saddle, those temperature fluctuations would display characteristic signatures, specific patterns in their distribution and scale that would reveal the underlying geometry. What we've found is remarkable in its simplicity. Observed curvature is consistent with zero within measurement uncertainty. The universe appears to be flat, or so close to flat that any curvature is smaller than we can currently detect. Our measurements have become extraordinarily precise, narrowing the possible range of curvature to less than 1% deviation from perfect flatness. That means if the universe is curved at all, that curvature is extremely subtle, indicating either that space is truly flat and infinite, or that it's so enormously large that its curvature becomes detectable only at scales far exceeding what we can observe. It's like measuring a small patch of Earth's surface with increasing precision and finding it flatter and flatter, suggesting either that Earth is genuinely flat, which we know isn't true, or that it's much larger than the area you're measuring, which is the actual case. Scientists have also searched for another type of evidence that might reveal the universe's topology, looking for repeating patterns that would indicate space wraps around on itself. No repeating patterns appear in the observable universe, at least none that we've been able to detect. If the universe were finite and relatively small, if it looped back on itself at distances comparable to or smaller than the observable universe, we might see the same galaxies or galaxy clusters appearing in multiple locations in the sky, their light having reached us from different directions after wrapping around the cosmos. Imagine looking at a funhouse with mirrored walls. You'd see multiple reflections of the same objects, repeated images that tell you the space you're in is connected in unusual ways. Similarly, in a small finite universe, we might see cosmic structures repeated, the same patterns appearing in different parts of the sky because we're essentially seeing around the universe, observing the same regions from multiple paths. This rules out small wraparound topologies. If the universe connects back to itself at scales of tens of billions of light-years or less, we should be able to detect the evidence. The fact that we see no such repetitions, no matched pairs of galaxy clusters or distinctive patterns appearing in opposite directions, tells us that if space is finite and wraps around, it must do so at much larger scales. The loop, if it exists, must be so vast that light hasn't had time to travel around it even once during the entire history of the universe. If space is finite, it exceeds the observable universe many times over, perhaps hundreds or thousands of times larger in its total extent. The mathematical models make this constraint more specific. Some models require space to be hundreds of times larger than observable before the topology becomes compatible with our observations. If you imagine a universe that curves back on itself like the surface of a sphere, but that sphere is so enormous that the observable universe fits inside it hundreds of times, you begin to appreciate the scales involved. We're not talking about a cozy, wraparound cosmos where you might encounter the back of your own head if you looked far enough. We're talking about a finite space so vast that it effectively behaves as infinite within any distance we can observe or will ever be able to observe, even in principle. One specific search that scientists have conducted involves looking for matched circles in the sky, a signature that certain topologies would produce in the cosmic microwave background. In some finite universe models, particularly those with more complex topologies, you might see circular patterns where the temperature fluctuations match perfectly, indicating that you're looking at the same region of space from two different directions, seeing around the universe along paths that reconnect. No matched circles in the sky have been detected despite careful searches of the cosmic microwave background data. This non-detection places stringent limits on non-trivial topologies. Many of the more exotic ways that space could connect back to itself, the interesting mathematical possibilities that would give the universe unusual properties, are ruled out by this absence of evidence. If such topologies exist, they must operate at scales so large that their signatures fall outside our observational reach. Given all these constraints, flat, simply connected space remains favored by the data. Simply connected means there are no loops or shortcuts, no paths that circle back to their starting point, no wormholes or handles or complex geometric features connecting distant regions. It's the most straightforward topology, the one where space extends uniformly in all directions following Euclidean geometry without any unusual connections or boundaries. This is the universe that Occam's razor would suggest, the simplest possibility consistent with our observations. It's also the universe that most naturally emerges from our leading theories of cosmic inflation, the period of rapid expansion in the first fraction of a second after the Big Bang that would have stretched space to enormous scales and flattened any initial curvature to imperceptible levels. Yet we must acknowledge that more exotic shapes remain theoretically possible. Our observations can only rule out certain possibilities. They cannot prove with absolute certainty that the universe is infinite and simply connected. There could be topological features or curvature operating at scales far beyond the observable universe, structures so vast or so distant that no evidence of them has reached us yet. The universe might connect to itself in ways we haven't imagined, following geometric rules that seem bizarre or counterintuitive but remain mathematically valid and physically possible. Perhaps there are regions where space is stitched together like patches on a quilt, or dimensions that fold and curve through higher dimensional spaces we can't perceive. These possibilities aren't favored by current data, and there's no particular reason to think they're true, but they can't be definitively excluded. The honest scientific position is one of measured confidence. We can say with great certainty that the universe is very flat, that it shows no evidence of small-scale topology or significant curvature within the observable region. We can say that if it's finite, it's vastly larger than what we can see. We can favor the simplest models that fit our data. But we must also admit the limits of our knowledge. We're observing a finite patch of what may be an infinite expanse, or a tiny corner of a finite but incomprehensibly large whole. Future observations might reveal new patterns or signatures that change our understanding. New theoretical insights might suggest possibilities we haven't considered. For now, we navigate between what we can measure and what we can imagine, constrained by data but aware that reality might extend far beyond our current ability to observe or comprehend. The shape of the universe remains one of the deepest questions in cosmology, a question we've narrowed considerably but haven't yet answered with finality. In the first moments after the Big Bang, something extraordinary happened, an event so dramatic and so brief that it reshaped the entire cosmos before the universe was even a second old. Inflation theory proposes an early phase of exponential expansion, a period when space grew at an almost incomprehensible rate, doubling in size repeatedly over intervals so short that trillions of these doublings could occur in less time than it takes light to cross the nucleus of an atom. This wasn't the gradual expansion we observe today, the steady stretching of space described by Hubble's law. This was explosive growth, a runaway process where space expanded faster and faster, driven by a peculiar form of energy that pushed outward with tremendous force, multiplying the size of the universe by enormous factors in an incredibly brief span. The numbers involved defy easy comprehension. During inflation, which may have lasted somewhere between a tiny fraction of a second and perhaps a few seconds depending on the specific model, the universe grew by a factor of at least 10 to the 26th power, and possibly far more. That's a 1 followed by 26 zeros, an expansion that took something smaller than a subatomic particle and stretched it to dimensions vastly larger than the observable universe we see today. Imagine a grain of sand suddenly expanding to become larger than the entire visible cosmos, and you begin to approach the scale of transformation that inflation describes. And this happened everywhere simultaneously, not just in one location but throughout all of space, creating the vast expanse we inhabit from an initial region so tiny it would have been invisible under any microscope. One of the primary motivations for inflation theory is that inflation makes any initial curvature extremely small. In the earliest moments of the Big Bang, before inflation occurred, space might have had significant curvature. It might have been curved like a sphere or saddle, bent and warped in ways that would have made the geometry of the universe distinctly non-Euclidean. But exponential expansion has a remarkable effect on curvature. When you stretch something enormously, any curvature it had becomes progressively less noticeable. Think of a balloon with a pattern drawn on its surface. When the balloon is small, the pattern is clearly curved, following the spherical shape. But inflate that balloon to enormous size, and any small patch of its surface begins to look flatter and flatter. The curvature is still there mathematically, but it becomes so gradual, so subtle across the visible region, that it appears essentially flat to any observer examining a limited area. This explains why the universe appears flat today. Our measurements show the universe is geometrically flat to within a fraction of a percent, a precision that seems almost too perfect to be coincidental. Why should the universe have exactly the right amount of matter and energy to produce zero curvature? Why not slightly more, creating positive curvature and a closed universe, or slightly less, creating negative curvature and a saddle-shaped geometry? Inflation provides an answer. It doesn't matter what the initial curvature was. Inflation stretched space so dramatically that any initial curvature was diluted to negligible levels. We observe a flat universe not because conditions were precisely tuned at the Big Bang, but because inflation took whatever conditions existed and stretched them smooth, ironing out curvature like pulling wrinkles from a sheet. This same process leads to another profound prediction. Inflation predicts a universe much larger than observable space. If inflation expanded the universe by such enormous factors, the region we can observe, limited by the speed of light and the age of the cosmos, represents only a tiny fraction of the total. The entire space may span vastly more than the observable radius, perhaps thousands or millions or even infinitely many times larger. We find ourselves in a situation analogous to an ant on the surface of Earth trying to determine the planet's full size while only being able to explore a few square inches. The ant might measure those square inches very carefully, determining their topology and geometry with great precision, but would have no direct way to know whether the surface extended for miles or millions of miles beyond its observable range. But inflation does more than solve the flatness problem and suggest a vast universe. It also has the effect of erasing evidence. Inflation erases evidence of pre-inflationary conditions, wiping the slate clean in a way that makes certain questions about the universe's earliest moments fundamentally unanswerable. Any structures, patterns, or irregularities that existed before inflation began were stretched to such enormous scales that they now lie far beyond our observable horizon. Imagine writing a detailed message on that balloon before inflating it. After expanding it by a factor of 10 to the 26th or more, the letters of your message would be spread so far apart that each individual letter would be larger than the entire observable universe. No observer could see enough of even a single letter to recognize it as writing, let alone read the full message. This means that earlier cosmic history may be fundamentally unobservable, not just difficult to observe with current technology but impossible in principle. There's a limit to how far back we can see, not just because of distance or time, but because inflation has permanently removed certain information from our accessible region of space. We can study the universe from shortly after inflation ended, when normal expansion resumed and the conditions we observe today began to take shape. We can theorize about what might have happened before inflation, We can construct models and mathematics that describe pre-inflationary physics. But we may never be able to test those theories observationally because inflation has carried the evidence beyond our reach, stretched it across distances we can never traverse or observe, encrypted it in a code we can never decode because we lack access to the full text. Yet inflation also created something, imprinting patterns on the universe that we can observe. Inflation also produces nearly scale-invariant fluctuations, tiny variations in density and energy that existed at quantum scales during the inflationary period and were stretched by expansion to cosmic sizes. These fluctuations were incredibly small, deviations from perfect uniformity of only about 1 part in 100,000, but they were crucial. In the early universe, regions that were slightly more dense had slightly stronger gravity, attracting more matter. Over billions of years, these subtle differences grew through gravitational amplification, pulling matter together into increasingly concentrated structures. These seeded galaxies and cosmic structure, providing the initial irregularities from which everything we see today eventually formed. Without these fluctuations, without the tiny density variations imprinted during inflation, the universe would have remained perfectly uniform. Matter and energy would have been spread evenly through space with no concentrations, no gathering points where gravity could begin accumulating material. There would be no galaxies, no stars, no planets, no structures of any kind, just a diffuse cosmic fog of particles distributed uniformly through an expanding void. The fact that we exist, that structure exists, that the universe contains rich complexity rather than bland uniformity, traces back to those quantum fluctuations during inflation, amplified to cosmic scales and given billions of years to evolve under the influence of gravity. What's remarkable is that these fluctuations have a specific character that inflation predicts. Their slight tilt matches observations. Scale invariant means the fluctuations have roughly the same amplitude at all size scales, but nearly scale invariant means there's a small deviation from perfect uniformity, a subtle trend where fluctuations are slightly stronger at some scales than others. This tilt, this gentle slope in the spectrum of fluctuations, is precisely what inflation theory predicts, and it's exactly what we observe when we map the cosmic microwave background radiation and measure the distribution of galaxies. The match between prediction and observation is one of the strongest pieces of evidence supporting inflation theory. It's not just that inflation explains why the universe is flat or why it's so large. It's that inflation makes specific, quantitative predictions about the patterns we should see in the cosmos, and those predictions align remarkably well with what our telescopes reveal. The universe bears the fingerprints of its inflationary birth, subtle but unmistakable signatures that tell the story of those first extraordinary moments when space itself grew faster than imagination, transforming the tiny into the vast and setting the stage for everything that would follow. The universe, for all its remarkable uniformity on large scales, is not perfectly smooth. Some observations challenge perfect isotropy, revealing features in the cosmos that seem to suggest directional preferences or unusual patterns that don't quite fit our expectations of complete uniformity. For decades, our measurements of the cosmic microwave background radiation have grown increasingly precise, allowing us to map temperature variations across the entire sky with extraordinary resolution. Most of what we see confirms our standard models beautifully. The patterns are consistent with random quantum fluctuations stretched to cosmic scales, displaying statistical properties that match inflation theory's predictions almost perfectly. But almost is not quite the same as exactly, and in the subtle deviations from perfect randomness, we find hints that something might be slightly unusual about our universe. Large-scale CMB anomalies include power asymmetry, an observation that the temperature fluctuations appear slightly stronger in one hemisphere of the sky than in the opposite hemisphere. When we divide the cosmic microwave background into two halves, drawing an imaginary line across the sky, we find that the variations aren't quite equal on both sides. One hemisphere shows fluctuations that are roughly 10% larger in amplitude than the other. This might not sound like much, but it's unexpected. If the universe is truly isotropic, truly the same in all directions, we shouldn't see this kind of hemispherical asymmetry. Temperature fluctuations should be statistically identical no matter which direction we look. The fact that they're not, that there seems to be a preferred direction in the universe where fluctuations are somehow different, is puzzling. Even more intriguing are the quadrupole and octuple alignments, technical terms that refer to specific patterns in the cosmic microwave background when analyzed using a mathematical technique called spherical harmonics. The quadrupole represents the largest scale temperature variation across the sky, while the octuple is the next scale down. These patterns should be randomly oriented relative to each other if the universe is isotropic and the fluctuations arose from random quantum processes. But observations show they're aligned, pointing in roughly the same direction, defining what some researchers have called an axis of evil through the cosmos. This alignment is unexpected enough that its probability of occurring by chance is fairly small, though not so small that we can rule out random coincidence entirely. Adding to these puzzles is a feature that has captured significant attention. The CMB cold spot stands out against expected randomness, a region of the sky roughly 5 degrees across where the cosmic microwave background is measurably colder than its surroundings. Cold spots should exist, of course. The temperature of the CMB varies naturally from place to place by tiny amounts, and pure statistics tells us we should see some regions that are unusually hot or cold just by chance. But the CMB cold spot is larger and colder than we'd typically expect. It's not dramatically outside the bounds of possibility, but it sits near the edge of what random fluctuations would produce, making it statistically unusual though not impossible. Researchers have proposed various explanations. A massive supervoid may contribute to the cold spot, a vast underdense region of space between us and the cosmic microwave background where there are fewer galaxies than average. Light traveling through such a void experiences a subtle effect. As photons fall into the void, they gain energy and become slightly bluer. As they climb out the other side, they should lose that energy and redshift back to their original wavelength. But if the void is expanding due to cosmic expansion, its gravitational field weakens over the time it takes light to traverse it, and the photons don't lose quite as much energy climbing out as they gain falling in. The net result is a slight cooling effect on the cosmic microwave background light that passes through the void, potentially explaining at least part of the cold spot's unusual coldness. Yet the explanations are not entirely satisfying. Some anomalies may arise from structures beyond the observable horizon, regions of space that we cannot directly observe but whose gravitational influence might affect the large-scale structure in ways we haven't fully accounted for. If the universe beyond our horizon is not perfectly uniform, if there are variations in density or energy at scales larger than we can see, those variations might create subtle directional effects in the observable universe, imprinting patterns that appear anomalous when we assume perfect isotropy extending infinitely in all directions. It's like trying to understand weather patterns in your local area without being able to see the continent-scale pressure systems that drive them. You might observe winds that seem to have a preferred direction and wonder why, not realizing that forces beyond your visible horizon are creating those patterns. Alternatively, and perhaps more prosaically, others may be statistical flukes. When you search for patterns in data, especially when you look for many different types of patterns across many different scales, you inevitably find some things that appear unusual purely by chance. This is a well-known problem in statistics called the multiple comparisons issue or the look elsewhere effect. If you perform 100 different statistical tests on random data, you'd expect about 5 of them to show significant results at the 95% confidence level simply by luck, even though nothing real is happening. The cosmic microwave background is an incredibly rich data set, analyzed in countless ways by hundreds of researchers over decades. It would be surprising if we didn't find some features that appeared statistically unlikely. The scientific community remains uncertain about how seriously to take these anomalies. Future surveys aim to clarify these anomalies through more precise measurements and by examining the universe in complementary ways. Newer satellites and ground-based telescopes with greater sensitivity might reveal whether the patterns we see are robust features that persist under scrutiny or artifacts that disappear with better data. Studies of galaxy distributions on the largest scales, measurements of gravitational lensing that map the distribution of dark matter, and observations of how galaxies move through space might provide independent evidence for or against the reality of these anomalies. If the asymmetries and alignments are real, they should show up in multiple datasets. If they're flukes, they should remain confined to specific types of observations. Adding another layer to the mystery, parity violations in CMB patterns have been reported. Parity symmetry is the idea that physics should look the same if you flip everything in a mirror. The universe should be symmetric under this reflection, with no fundamental distinction between left and right. But some analyses of the cosmic microwave background suggest subtle violations of this symmetry, patterns that appear different from their mirror images in ways that shouldn't occur if the underlying physics is paritysymmetric. These reports are controversial, not universally accepted by the scientific community, and subject to ongoing debate about whether they represent real physical effects or artifacts of how the data is processed and analyzed. Their origin remains uncertain. If these anomalies are real, if they represent genuine features of the universe rather than statistical noise or systematic errors in our measurements, they would have profound implications. They might indicate new physics beyond our current understanding, perhaps violations of isotropy that point to underlying structures or fields that break the symmetry of space on the largest scales. They might suggest that our observable universe sits in a special location within a larger cosmos, perhaps near the edge of some vast structure or in a region with unusual properties. Or they might reveal limitations in our theoretical models, showing that the universe is slightly more complex than the simple, perfectly isotropic cosmos we've been assuming. For now, these features remain tantalizing hints, observations that don't quite fit the standard picture but aren't dramatic enough to overturn it, mysteries that hover at the boundary between the expected and the inexplicable, waiting for better data and deeper understanding to reveal their true nature. When we think about the shape of space, we usually imagine something straightforward, either infinite space stretching forever in all directions, or perhaps space that curves back on itself like the surface of a sphere. But mathematics allows for far more exotic possibilities. The universe's topology may be more complex than simple space, with connections and structures that go beyond mere curvature. Topology is the branch of mathematics that studies how spaces can be connected, how they might loop back on themselves or link distant regions in unexpected ways, independent of their geometric curvature. A flat piece of paper and a cylinder have the same geometry, both flat surfaces where parallel lines remain parallel, but they have different topologies. The cylinder connects back to itself in one direction while the paper doesn't. Similarly, the universe might be geometrically flat while still having a complex topology that creates unusual connections across space. If space has such unusual topology, we should be able to detect it through a striking prediction. Non-trivial topologies would produce repeating sky patterns, cosmic Hall of Mirrors effects where we'd see the same astronomical objects appearing in multiple locations. Imagine a universe shaped like a three-dimensional torus, the higher dimensional analog of a donut surface. In such a universe, traveling far enough in certain directions would bring you back to where you started, like the old video games where moving off one edge of the screen made you reappear on the opposite edge. Light would follow the same paths, wrapping around the universe and arriving from multiple directions. We might see the same galaxy cluster appearing twice in our telescopes, once in its actual location and again as light from that cluster took the long way around, circling through space's topological connections to arrive from a different direction. The search for such patterns has been thorough and systematic. Such effects have not been observed so far. Astronomers have examined the distributions of galaxies and the cosmic microwave background, looking for the telltale signs of repetition that would indicate topology. If the universe wrapped around at scales comparable to or smaller than what we can observe, we should see matching patterns, regions of the sky that look suspiciously similar because they're actually the same region viewed along different paths through space. The absence of these patterns tells us something important. If the universe has non-trivial topology, if it connects back to itself in unusual ways, it must do so at scales vastly larger than the observable universe, so large that light hasn't had time to traverse the loops even once during the entire cosmic history. Specific topological models make specific predictions. Flat torus models predict distinctive matched circles, particular patterns that would appear in the cosmic microwave background if space had this topology. A three-torus is like taking a cube and connecting its opposite faces. Exit through the top and you re-enter from the bottom, exit through the left side and you re-enter from the right, and so on in all three dimensions. If our universe had this topology, the cosmic microwave background would show circular regions where the temperature patterns matched perfectly, because we'd be seeing the same region of the early universe from multiple directions, light having wrapped around the cosmos before reaching us. These signatures have not been detected despite careful searches that could have revealed them if they existed at observable scales. The implications extend beyond mere pattern matching. Some models predict infinite self-images of observers, a profoundly strange consequence of certain topologies. In a finite universe with wraparound topology, light from any location can travel in multiple directions and, given enough time, complete multiple loops around the cosmos. This means that in principle, you could look out into space and see yourself, or at least see your galaxy, appearing multiple times at various distances and from various angles, each image representing light that took a different number of loops around the universe before arriving at your telescope. It's the ultimate cosmic echo, where your own past radiates back to you from multiple directions. No such duplicates have been observed. We don't see our galaxy or our local group of galaxies repeated at other locations in the sky, which again constrains any possible topology to scales far exceeding what we can observe. The mathematical possibilities are richer than you might expect. 10 possible flat spatial manifolds exist mathematically, 10 different ways that three-dimensional flat space can be connected to itself while maintaining Euclidean geometry. These aren't just abstract constructions. They're legitimate solutions to the equations of general relativity, valid ways that the universe could be structured. They have names like the three-torus, the 6 orientable manifolds, and the 4 non-orientable manifolds. Non-orientable means that traveling certain paths through such a space would bring you back reversed, like you'd passed through a mirror, your left hand having become your right hand. These spaces are difficult to visualize because they require connections through higher dimensions, but they're mathematically well-defined and physically possible. Yet when we compare these possibilities to what we actually observe, the verdict is clear. Observations favor the simplest geometry, the most straightforward topology where space is simply connected, extending in all directions without looping back or connecting to itself in unusual ways. There's no evidence for the complex patterns these exotic topologies would produce. The universe appears, as far as we can tell, to be exactly what it seems. Flat or nearly flat space that either continues infinitely or, if finite, wraps around only at scales so enormous that we cannot detect the wraparound within our observable region. Occam's razor suggests we should favor this simpler explanation in the absence of evidence for something more complex. But we must be careful not to confuse favored by current observations with definitely true. Topology remains an open question, one that may never be fully resolved given the fundamental limitations on what we can observe. The universe beyond our horizon remains inaccessible to direct measurement, and if topological connections exist at those vast scales, they might be forever beyond our ability to detect. We're making observations from a single location, limited to a finite region of space, trying to infer the structure of something that might extend infinitely or wrap around in ways we cannot perceive from our restricted vantage point. Future observations might change the picture. More sensitive measurements of the cosmic microwave background, more complete catalogues of galaxy positions extending to greater distances, or theoretical insights that suggest new ways to search for topological signatures might reveal patterns we've missed. Or we might find ways to constrain topology indirectly, through its effects on cosmic evolution or structure formation, even if we cannot directly observe the wraparound patterns. But it's equally possible that this question will remain permanently unanswered, that the true topology of the universe will be something we can speculate about and model mathematically but never definitively determine through observation. We find ourselves in the curious position of living in a cosmos whose full structure may be hidden from us, not by any deliberate concealment but simply by the vastness of space and the finite time that light has had to travel since the beginning. The universe keeps its ultimate secrets not through complexity but through sheer scale, presenting us with a view that is both astonishingly detailed within our horizons and frustratingly limited beyond them. Inflation, that period of extraordinary exponential expansion in the universe's first moments, might not have been a one-time event that happened and ended everywhere simultaneously. Eternal inflation predicts endlessly growing space, a scenario where the inflationary process, once started, continues forever in at least some regions of the cosmos. This is one of the most mind-bending implications of inflation theory, emerging naturally from many versions of the mathematics that describe how inflation works. The basic idea is that inflation is driven by a special field, sometimes called the inflaton field, which exists throughout space with a certain energy. When this field has high energy, it drives rapid expansion. When the field's energy drops to lower values, inflation ends and normal expansion takes over. But quantum mechanics introduces randomness into this process. In some regions, the field drops to lower energy and inflation stops. In other regions, quantum fluctuations kick the field back up to higher energy, and inflation continues. The result is that inflation may never end globally, even though it ends locally in many places. Picture a vast expanse of space inflating exponentially, doubling in size over and over. Within this inflating region, quantum fluctuations cause some patches to stop inflating. But the regions that continue inflating grow so rapidly that they more than compensate for the patches that stop. The overall volume of inflating space keeps increasing without limit, even as countless individual regions drop out of the inflationary phase. It's like a forest where trees are constantly sprouting new branches, and while individual branches might stop growing, the tree as a whole keeps expanding because new branches emerge faster than old ones stop. When inflation stops in a particular region, that region undergoes what's called reheating, where the energy driving inflation converts into particles and radiation, creating hot, dense conditions similar to what we think of as the traditional Big Bang. Local regions stop inflating and form bubble universes, each one a pocket of normal space carved out of the eternally inflating background. Our observable universe would be inside one such bubble, a region where inflation ended about 13.8 billion years ago, allowing matter and energy to cool, structures to form, and eventually giving rise to galaxies, stars, planets, and conscious observers. But beyond our bubble, inflation might still be continuing, creating more space, and within that expanding space, more bubbles would constantly be forming, each one its own universe with its own Big Bang moment, its own timeline, its own evolution. What makes this scenario particularly fascinating is that each bubble could have different physical constants. The properties we think of as fundamental, things like the strength of gravity, the mass of electrons, the speed of light, might not be truly fundamental at all. They might be environmental variables, features that take on different values in different bubble universes depending on exactly how the inflaton field and other quantum fields settled into their low energy states when inflation ended. In our bubble, the electron has a particular mass and charge. In another bubble, those values might be different. The fine structure constant, which determines the strength of electromagnetic interactions, has one value here but might have another value there. These variations wouldn't be arbitrary. They'd be determined by the underlying physics, by how different quantum fields interact and what stable configurations they can settle into. But the result would be a vast cosmos containing countless bubble universes, each with its own local physics, its own set of constants, its own unique combination of properties. Our universe may be one such bubble among countless others, a single pocket of spacetime in an eternally inflating megaverse. We find ourselves here not because our bubble is special or central, but simply because the physical constants in our bubble happen to allow for the formation of complex structures, stars that can forge heavy elements, planets where chemistry can become complex enough to generate life, and eventually conscious beings capable of asking these questions. In bubbles where constants took on different values, perhaps no stars form, or stars form but burn out too quickly, or matter never clumps together to create structures at all. Those bubbles would be sterile, devoid of observers, while bubbles like ours, rare though they might be in the broader multiverse, would inevitably be where observers find themselves, simply because those are the only bubbles where observers can exist. In this framework, there is no global edge in eternal inflation. The concept of an edge becomes meaningless when space is constantly creating more of itself without limit. There's no boundary to the inflating region because it's always growing, always expanding, always producing new space faster than you could ever traverse it. Any edge you might imagine reaching would recede faster than you could approach it. But boundaries exist only between inflating and non-inflating regions, the interfaces where bubbles meet the eternally inflating space around them or where different bubbles might encounter each other. These boundaries aren't edges of space in the traditional sense. They're transitions between different phases, regions where the physical conditions change from one state to another, like the boundary between water and ice in a partially frozen lake. This raises an intriguing observational possibility. Bubble collisions could leave observable imprints in our cosmic microwave background or in the large-scale distribution of galaxies. If our bubble universe had collided with another bubble at some point in the past, after our inflation ended but early enough in cosmic history, the collision might have created a distinctive pattern, perhaps a circular feature in the sky where the temperature or density differs from surrounding regions, a cosmic bruise marking the point where another universe bumped into ours. Physicists have calculated what such collision signatures might look like and have searched for them in the data we've collected. No definitive evidence has been found. The searches have been thorough, examining the cosmic microwave background for unusual circular patterns or asymmetries that might indicate a bubble collision. Some candidates have been proposed, features that looked potentially interesting, but none have held up under scrutiny as definitive proof of a collision. They all seem consistent with random fluctuations or other astrophysical effects, leaving us without clear evidence that our universe has collided with another. This doesn't mean bubble collisions haven't occurred. It's possible they happened too early or too far from our location to have left detectable imprints. Or perhaps our bubble has simply been isolated, floating in the eternally inflating space without encountering neighbors during the observable history of our cosmos. This brings us to an important caveat. Multiverse ideas remain speculative, sitting at the boundary between physics and philosophy. The concept emerges naturally from well-tested theories like inflation and quantum mechanics, and many physicists take it seriously as a potential description of reality. But it's extraordinarily difficult to test. By definition, other bubble universes are beyond our observable horizon, causally disconnected from us, their light unable to reach us because the space between us is expanding too rapidly. We might never be able to directly confirm that other universes exist. We might never detect another bubble or observe the eternally inflating space beyond our own pocket. This troubles some scientists, who argue that ideas we can't test aren't properly scientific, that physics should confine itself to questions that can be answered through observation and experiment. Others counter that we should follow the mathematics and logic wherever they lead, and if our best theories naturally predict a multiverse, we should take that prediction seriously even if we can't directly observe it. The debate continues, reflecting fundamental questions about what science is and how we should think about theories that make predictions beyond the reach of observation. For now, eternal inflation and the multiverse it predicts remain fascinating possibilities, consistent with what we know but unproven, ideas that expand our conception of reality while reminding us how much about the cosmos might forever remain beyond our ability to definitively confirm or deny. The fabric of space and time, which seems so solid and fundamental to our everyday experience, might be something else entirely at the deepest level of reality. Some theories suggest space is fundamentally emergent, not a basic building block of the universe, but rather something that arises from more fundamental entities and interactions, like how the wetness of water emerges from the collective behavior of countless individual molecules even though no single molecule is wet. This idea challenges our most basic intuitions about reality. We think of space as the stage on which physics plays out, the container in which events occur, existing independently and providing the backdrop for everything else. But perhaps space is more like temperature or pressure, a macroscopic property that emerges when you have many smaller things interacting, a useful concept at large scales that breaks down when you look too closely at the underlying structure. This possibility becomes more concrete when we consider the challenge of uniting quantum mechanics with gravity. Quantum gravity predicts a minimum length scale, a fundamental limit to how finely we can divide space before the very concept of distance stops making sense. This scale is called the Planck length, an almost incomprehensibly tiny distance of about 10 to the negative 35 meters, far smaller than any particle we can detect, smaller than an atom by about the same factor that an atom is smaller than a galaxy. Below this scale, classical spacetime breaks down. The smooth, continuous geometry described by Einstein's general relativity gives way to something else, a quantum foam where space and time fluctuate wildly, where the usual rules no longer apply, where asking about the precise location or duration of something becomes meaningless because space and time themselves lose their conventional meaning. At this fundamental level, the question shifts from what space is made of to what space emerges from. Spacetime may arise from quantum information, from patterns of entanglement and correlation between more basic quantum degrees of freedom. This idea has gained traction in recent years through work connecting quantum information theory with gravity. Entanglement is a quantum phenomenon where particles become correlated in ways that have no classical analog, their properties linked so that measuring one instantly tells you something about the other regardless of the distance between them. Recent research suggests that the geometry of spacetime, the very structure that determines distances and relationships between events, might emerge from patterns of quantum entanglement. Where entanglement is strong, space is connected and nearby. Where entanglement is weak, space is disconnected and distant. Space itself becomes a manifestation of quantum information, geometry arising from correlation. Different approaches to quantum gravity envision this emergence in different ways. Causal set theory models spacetime as discrete points, a fundamentally granular structure where the smooth continuum we perceive at large scales is actually composed of discrete, indivisible elements. In this picture, spacetime is like a digital photograph that appears continuous when viewed from far away but reveals individual pixels upon close examination. The points in a causal set are ordered by a causal structure, a network of relationships indicating which points can influence which other points, essentially defining what it means for one event to come before or after another. Spacetime, in this view, is the causal structure, and what we call geometry emerges from the statistical properties of this discrete network when you have vast numbers of points. Another approach, loop quantum gravity, takes the mathematical framework of general relativity and applies quantum principles directly to the fabric of space itself. In this theory, space at the Planck scale consists of tiny loops and networks, a kind of quantum weave where the geometry is quantized, coming in discrete units like the energy levels of an atom. One of the most remarkable predictions of loop quantum gravity is that it replaces singularities with bounces. In classical general relativity, we encounter singularities, points where the mathematics breaks down and physical quantities become infinite, most notably at the center of black holes and at the Big Bang itself. These singularities have always been troubling, suggesting that our theories are incomplete because they predict their own failure. Loop quantum gravity suggests that quantum effects become important near these would-be singularities, preventing infinite densities and infinite curvatures, instead creating quantum bounces where matter and energy reach extremely high but finite values before rebounding. This leads to a profound implication about cosmic origins. The Big Bang may not be a true beginning but rather a transition, a bounce from a previous phase of cosmic existence. In some versions of loop quantum cosmology, the universe undergoes cycles of expansion and contraction, bouncing at maximum density rather than collapsing into a singularity or emerging from one. Our Big Bang might have been a big bounce, the moment when a previous contracting universe reached its quantum limit and rebounded into expansion, creating the universe we observe today. Time wouldn't have started at the Big Bang in this scenario. It would extend backward through the bounce into a prior phase, making the question of what came before the Big Bang not only meaningful but potentially answerable through physics rather than metaphysics. These ideas push us toward a deeper revision of our concepts. Time and space could emerge from deeper rules, from relationships and structures that don't themselves exist in space or time because they're what gives rise to space and time in the first place. This is conceptually challenging because all our language and intuition are rooted in spatial and temporal concepts. We struggle to imagine or describe something that exists outside of space and time, yet that might be exactly what underlies reality at its deepest level. It's like trying to explain color to someone who has never seen, or asking what's north of the North Pole. The question assumes a framework that might not apply to the thing you're asking about. Evidence for these ideas comes from unexpected places. Event horizons encode information on surfaces, a discovery that emerged from studying black holes and has profound implications for the nature of space. Stephen Hawking's work on black hole thermodynamics showed that black holes have entropy, a measure of information content, and that this entropy is proportional not to the volume of the black hole but to its surface area, specifically to the area of its event horizon. This was surprising. We normally think of entropy as being related to the number of possible configurations of things inside a volume, suggesting entropy should scale with volume. But black holes apparently encode all their information on their surface, suggesting that the three-dimensional volume might be somehow secondary to the two-dimensional boundary. This supports the holographic principle, the idea that all the information contained in a volume of space can be encoded on the boundary of that region, like how a hologram encodes three-dimensional information on a two-dimensional surface. If true, this principle suggests something radical about the nature of reality, that what we perceive as three-dimensional space might be a kind of projection or emergence from information stored on a lower-dimensional surface. The universe might be, in some sense, a hologram, a three-dimensional experience arising from two-dimensional information, challenging our assumption that the dimensions we perceive directly are the fundamental ones. These ideas remain at the frontier of theoretical physics, unproven but tantalizing, suggesting that space and time as we know them are not the final story but rather chapters in a deeper tale about the nature of reality, one we're only beginning to read. Black holes have revealed unexpected connections between gravity, thermodynamics, and information, connections that hint at something profound about the nature of space itself. Black hole horizons obey entropy area laws, a relationship discovered through theoretical work in the 1970s that showed black holes behave remarkably like thermodynamic systems. Every black hole has a temperature, incredibly cold for stellar mass black holes, but nevertheless a real, calculable temperature inversely proportional to the black hole's mass. And with temperature comes entropy, that fundamental measure of disorder or information content that appears throughout physics. What's remarkable is that a black hole's entropy is proportional to the area of its event horizon measured in Planck units, not to its volume as you might expect. A black hole twice as wide has 4 times the surface area and therefore 4 times the entropy, but 8 times the volume. The information scales with the surface, not the interior. These laws limit information density in space in a fundamental way. The maximum amount of information you can pack into any region of space is determined not by how much volume that region has, but by how much surface area its boundary encompasses. Try to cram more information into a region than this limit allows, and the region will collapse into a black hole whose event horizon has exactly the surface area needed to accommodate that information. You can't cheat the limit by making the region smaller or denser. Compress information too much and you create a black hole, which then has its own surface area determined by how much information it contains. This suggests something deep about the nature of space and information, a relationship that constrains what's physically possible in ways we're still working to fully understand. The holographic principle suggests volume information lives on boundaries, extrapolating from black hole physics to make a bold claim about all of space. If black holes encode their information on surfaces, perhaps all volumes of space do the same. Everything happening within a region, all the particles and fields and interactions, all the complexity and structure, might ultimately be describable in terms of information encoded on that region's boundary. The three-dimensional world we experience would then be like a holographic image, appearing three-dimensional but actually encoded in 2 dimensions. This doesn't mean the universe is literally a hologram in the everyday sense of a fake projection. Rather, it suggests that the fundamental description of physics lives on boundaries, and the interior volumes we perceive emerge from that boundary information. This idea connects gravity and quantum theory in ways that have proven incredibly fruitful for theoretical physics. The most concrete realization comes from something called the AD-SCFT correspondence, a mathematical relationship discovered in string theory that precisely connects gravitational physics in one space to quantum field theory on that space's boundary. It's like finding 2 completely different languages that turn out to be perfect translations of each other, allowing physicists to solve hard problems in one framework by translating them to the other framework where they become easier. This correspondence strongly suggests that holography isn't just a curious mathematical trick but reflects something fundamental about how gravity and quantum mechanics relate to each other, offering clues toward a complete theory of quantum gravity. The implications extend beyond black holes. Cosmology may also obey holographic bounds, with the entire observable universe potentially describable in terms of information on a cosmological horizon. If the holographic principle applies universally, then all the galaxies and stars and planets we observe, the entire cosmic web of structure, everything within our observable sphere might be encoded on the boundary of that sphere. This raises fascinating questions about the nature of the early universe and what limits might exist on cosmic information content. Some cosmological observations, particularly measurements of entropy in the cosmic microwave background, show intriguing consistency with holographic bounds, though this remains an active area of research rather than settled science. These modern ideas about space and information connect to older questions about cosmic origins. No boundary proposals eliminate initial edges of time, suggesting that the universe doesn't actually have a beginning in the traditional sense of a first moment. Stephen Hawking and James Hartle developed one such proposal, arguing that asking what happened before the Big Bang is like asking what's south of the South Pole. The question assumes a framework, a notion of before, that doesn't apply. In their model, the universe may have no beginning boundary, not because it's infinitely old but because time itself emerges gradually from a more fundamental quantum state. Near what we call the Big Bang, time becomes increasingly space-like, blending with spatial dimensions in ways that eliminate any sharp starting point. Euclidean geometries smooth the Big Bang in these models by treating time as another dimension mathematically similar to space in the very early universe. In everyday physics, time is fundamentally different from space. You can move forward and backward through space, but only forward through time. Time has an inherent directionality that space lacks. But in certain mathematical formulations of quantum gravity, Particularly when describing the very beginning of the universe, this distinction blurs. Time can be treated as if it were a spatial dimension, using what physicists call Euclidean time. In this framework, the Big Bang singularity is smoothed out, replaced by a rounded geometry without sharp edges or beginnings, like the smooth surface at the South Pole rather than a point where coordinates become undefined. Alternatively, other models connect cosmic cycles across eons, proposing that the universe undergoes repeated cycles of expansion and contraction or transitions from one phase to another. Roger Penrose's conformal cyclic cosmology suggests that the universe goes through infinite cycles, each one beginning with what looks like a Big Bang but is actually a transition from the previous cycle's far future. In his model, the infinite expansion of one eon becomes the Big Bang of the next through a conformal transformation, a mathematical rescaling that connects vastly different scales. Other cyclic models involve bounces, where a contracting universe reaches a minimum size determined by quantum gravity effects and then rebounds into expansion. These models eliminate the need for an absolute beginning, pushing the question of ultimate origins back infinitely or making it irrelevant by having the universe exist eternally in a cycle. Yet for all our theorizing and observing, for all the equations we've written and the data we've collected, a fundamental truth remains. Whether space truly ends remains unknown. We've mapped the observable universe, measured its expansion, determined its geometry to high precision, found it consistent with flatness and possibly infinite extent. We've developed theories that describe how space might emerge from more fundamental structures, how information might be encoded on boundaries, how time might not have a beginning. But these remain theoretical possibilities, mathematical frameworks that fit our observations without being definitively proven. The universe might extend infinitely in all directions, an endless expanse of galaxies and structures beyond our horizon, continuing forever without boundary or edge. Or it might be finite but vastly larger than we can observe, curving back on itself at scales we cannot detect, creating a closed but boundaryless cosmos. Or it might have exotic topology, connecting to itself in ways we haven't imagined. Space itself might be an emergent phenomenon, a useful description at our scale that breaks down into something unrecognizably different at the Planck scale. The Big Bang might be a true beginning, or a bounce, or a transition, or a meaningless concept rendered obsolete by quantum effects that eliminate the notion of a first moment. We live in an era of unprecedented understanding, able to describe the universe's evolution from fractions of a second after the Big Bang to the present day with remarkable accuracy. We know the universe's age, its composition, its expansion history, its large-scale structure. Yet the deepest questions remain open. Does space end? Did time begin? What lies beyond our horizon? These questions sit at the boundary of physics and philosophy, accessible to scientific investigation yet possibly forever beyond definitive answer. We observe from a single point in space and time, with access to only a limited region of what might be infinite, trying to infer universal truths from local measurements. It's both the greatest challenge and the greatest adventure of science, this attempt to understand everything from our tiny, precious vantage point in the cosmos, knowing that reality might extend far beyond what we can ever hope to observe, yet compelled by curiosity to ask the questions anyway and follow the evidence as far as it can lead us into the unknown.